All right. Good morning. Okay, so just a quick look at our Moodle page here. So we're going to finish section 5.3, which is we're going to finish off by looking at the p-value approach to hypothesis testing. It is included on the quiz. So I did post assignment 8, which is really just a quick, well, it's not quick, but it's only 3 questions. So it's not too bad to get you to practice those a little bit. Okay, and so I took a screenshot here already, and I'm going to bring that into our notes. And maybe I'll just crop this here. Like that. How about that? Okay. So for tomorrow, the quiz opens. It's the same as the first quiz, right? Where you have the whole weekend to do it. So it'll open in the morning, and you could use our class time to do it, but you don't have to. And I'll make more notes about the quiz once I've posted it, but it's in right now. So we'll be available in the morning until Sunday at 11:59. So you can, and it's a 50-minute timed quiz. Just like the other one. I've tried to make it not quite so long, but just keep your pace up. Okay. You'll have to submit your work. It's not for marks, but if you do want me to go back and check any of your work, then of course you have to submit it within the 10 minutes. Okay, and so you'll have to submit your written work. Work within 10 minutes. Of completing the quiz. Otherwise, it won't be eligible for part marks, right? If you ask me to. So I'm not going to do the checking this time. I did the checking for the first one, mostly to show you kind of the things that I would give marks for. And then so it's up to you to check your quiz afterwards and check it against your written work. And if you find something where, oh, I think she might be able to give me more marks here, then you let me know and I go in and I check, okay? Otherwise, it's very time consuming. Okay, so otherwise, I won't be able to give part marks. So of course, if you haven't submitted anything, then there's nothing for me to look at, and that the grade that you get is just the grade that you get, and maybe you're fine with that, right? Then you don't have to upload your work. Okay, so assignment 8 is included on quiz number 2. Right, it's only 3 questions. And you've got more time than quiz number 2 to do it, but I would probably do it before you do the quiz just to make sure that you're on top of things. Okay. All right, and so for next week, I want you to start reading chapter 6, okay, specifically 6. So we've covered a lot of 6.1 in chapter 5 where we lay out the groundwork. And so that's going to be for a single proportion. And then we move on to, well, what if I want to compare 2 proportions? So I have 2 samples and I want to compare the proportions. And that sounds like a reasonable thing to want to do, right? And so that's what we're going to do in section 6.2. And then in 6.3, we compare more than 2 proportions, right? So we just kind of build on this, and then Chapter 6, only chapter 6 is on quiz number 3. So you can see how important that material is, because it's all, I want to say that's what I decided. Yeah, quiz 3 is on chapter 6. Yeah. So for next week, start reading chapter 6. Okay. That way, when we talk about it, it's not the first time that you're seeing it. Okay, so let's see here. Anything else that I've forgotten? I don't think so. So today, or Backtrack, last day we finished talking about hypothesis testing with a confidence interval. Now, there are some drawbacks, right, to using a confidence interval to test the hypothesis. And so today, I'm going to introduce the more formal hypothesis testing approach using p-values. But just as a little bit of review, right? We introduced hypothesis testing, and I guess I shouldn't capitalize that, it's just a word, hypothesis testing, which I'll abbreviate HT, okay, using the confidence interval approach. Using the confidence interval approach. Now, confidence interval, I typically abbreviate, oh, I made my bracket my C as well. I typically abbreviate CI. So we introduced hypothesis testing using the confidence interval approach. Okay. But the confidence interval approach has some drawbacks. Okay. But the CI approach has some drawbacks. Okay. The first one being you can't publish it in an academic journal, for example. It won't be accepted. And so it's not formal enough. Okay, so it's not a formal hypothesis test, right? So can't use in journals, although there is some debate going on that says, well, maybe we should be using confidence intervals instead of p-values. But for right now, if you are in the biology section of this course, then don't even bother. You're going to be using the p-value approach. But also if you're reading, papers and journals and stuff like that, then they're not going to really use the confidence interval approach to test the hypothesis. They'll include confidence intervals, but not to test the hypothesis. So it's not a formal hypothesis test, so you can't publish something using the confidence interval. Okay. The second one is that it really doesn't tell us how extreme the observation is. So you can look at the interval and you can compare it to your hypothesized value or your null value, and you can see if it's in there or not, but it's really hard to tell how far away that interval is from the hypothesized value, right? Because it's not necessarily linear, right? And so it's hard to know how extreme our observation was. Hard to know how extreme our observation is, right? All we have is really, we look at the interval, is the null value inside or outside the interval, and that's what we base our conclusion off of, right? If it's in the interval, then the null hypothesized value is contained in that 95% confidence interval, and that's fine. So then the null value is a plausible value, right? If it's outside the interval, then that's what we say gives us evidence against the null hypothesis and say, well, we're 95% confident the interval's over here, but if the null value is outside there, then I have enough evidence to reject H naught. Okay. And then the third drawback is that we're only able to do a two-sided test. Okay, so what that means is we can only test to see if P is not equal to some null value. Okay, so it comes down to the alternative hypothesis. So we can only do a two-sided hypothesis test, which is H naught is that P is equal to P naught, and HA is that P is not equal to P naught. Okay, so the two-sided is this not equal to, okay? Where sometimes we want to know if the population proportion is significantly less than some value, or maybe if it's significantly more than some value, right? And so, but we can't do that with a confidence interval. So we can only see if it's not equal to that null value. Okay? And that's because we've built an interval, right? And so, so it's going to be a two-sided test. Okay? So to get around all these, we introduce the p-value approach. So it wasn't really review, but it was talking about what we learned last day. So I'll call that the end of our review. Maybe I should add one thing. I said it, but I didn't write it down. So let's write it down. So in the confidence interval approach, right? How do we draw our conclusion, right? We compare the null value to the interval to either reject the null hypothesis or fail to reject the null hypothesis, right? You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. So in the confidence interval approach, we compare the null value which is your P naught, right? This P naught is the null value. That's the value you want to compare your sample to. Okay. We compare the null value to the confidence interval. So we really only have two options here. Right, I'll draw my two options. They're both going to be on a number line, and I've got some confidence interval, and it can be in the same location in both cases. Right, so here's my confidence interval, and here's my confidence interval. If my null value, so if P naught is outside that interval, then I have enough evidence to reject H naught. H naught says that P is basically P naught, right? It doesn't have to be exactly equal to, but it's not significantly different from P naught. Okay, whereas here, these are all the reasonable values that we've found. If P naught is outside there, then we have enough evidence. To reject H naught. Whereas if the null value is inside the interval somewhere, right, then we do not have enough evidence to reject H naught. No. I'm going to just bump that up one line so I can do my little end of review twiddle. I don't know what it's called. Okay, so that's how we draw our conclusion in terms of the confidence interval approach, right? And so that involves, I have to build well, first, okay, let's take it step by step. First, I have to set up my null and alternative hypotheses, and that establishes my null value. Then I have to build my confidence interval, right? And that is how I do my test, right? And then I actually compare my null value to my confidence interval, and then I can state my conclusion, right? So it was a lot of steps, but they all kind of make sense if you step back and think about what you want to do, right? You want to compare your null value to your confidence interval. We have sort of avoided checking our conditions for building a confidence interval, right? But we had to check our conditions, and we still should if we're going to build a confidence interval, right? So we have to check our conditions. And what were they? For independence, we have to have a randomly selected sample. And for a confidence interval, I have to have at least 10 successes and at least 10 failures in my sample, right? Then I can use the normal distribution, right? Which I rely on to build my confidence interval. Okay. So we're going to tweak those conditions just a little bit for when we're doing the p-value approach. Okay. So hypothesis testing with the p-value approach. Okay. Maybe I'll highlight this or something kind of important. Okay. Let's go through step by step and see where the differences are. We've already done this, but it doesn't hurt to do it again, right? Because when I was introducing the confidence interval approach, I would kind of mention the p-value approach alongside, but we didn't really go into any detail, and so that's what I want to do today. Okay. So step one, wait, zoomed in on me. Step one, oh my gosh. I started talking about it and then I forgot. Step 0, let's call it, is checking the conditions. Checking the conditions. It's not really part of the hypothesis testing, but it is part of being able to use the tools that we're about to use. So we have to check the conditions. So I call it step 0 because I'm kind of sneaking it in there. And so for the conditions, for the confidence interval approach, just for a recap, we had to have a randomly selected sample. And the optional one was that N had to be less than 10% of the population. So you have to have a randomly selected sample, or you have to assume that that you have a randomly selected sample. So checking the conditions, but we could also say stating the assumptions, right? Stating what the things that you're assuming are going on. So state the assumptions, right? If they're not mentioned in the question, then you have to assume them, okay? So I have to have a randomly selected sample, and the optional one is that N has to be less than 10% of the population. And I have to have N times P hat has to be greater than or equal to 10, and N times Q hat has to be greater than or equal to 10. Okay. And this is what we call the success failure condition. NP hat is the expected number of successes, or sorry, the observed number of successes, and NQ hat is the observed number of failures, right? So in this case, these are the observed successes and failures. Okay. Now, for the p-value approach, I'm going to do them side by side here. For the p-value approach, the first two are the same. So we have to have a randomly selected sample, and the optional N has to be less than 10% of the population. So the only one that's going to change here, if I'm using the p-value approach, is that I'm going to check a slightly different success failure condition. And that's all that changes. That can be confusing, right? And I'll mention why it is, but it's really just a matter of memorizing it and remembering that, okay, if I'm doing a confidence interval, then these are the conditions that I check. If I'm doing a hypothesis test, then these are the conditions that I check, right? And you're working open book, so make sure that you have that somewhere in your notes for when you're doing these problems. Okay, so you know what? I'm going to cheat and just copy this over. I know that's totally cheating. So these two are the same. And I should not use the same color here. Style. Let's do orange. Orangey glad. I used a different color. Okay, so then the success failure condition is going to change just ever so slightly. Instead of the observed successes and failures, it's going to be the expected successes and failures. And the expectation comes from the null hypothesis. Okay, and so what we have is we're going to check that NP naught is greater than or equal to 10, and NQ naught is greater than or equal to 10, right? And so here, these are the expected successes and failures. And remember, we've been saying that when we're doing hypothesis testing, we've been saying, okay, we do all our testing assuming the null hypothesis is true, right? And so that's the same for the conditions now. So the expected successes and failures, assuming the null hypothesis is true. Which is that H naught is that P is equal to P naught, right? And so that's where this little guy comes from, that P naught. Okay. So it's still called the success failure condition, but now we're checking the expected successes and failures instead of the observed successes and failures, right? And so from when we started introducing the proportion question, so recall that P hat comes from a normal distribution centered on P with a standard error of P and Q over N square rooted. We estimate P by P hat, right? Unless we have some hypothesized value for P, right? And so now in the p-value approach, that's when we're going to say, okay, I have a hypothesized value for P, so I'm going to use that instead. Right? That applies for hypothesis testing using the confidence interval as well. But because you're building a confidence interval, you can just check the confidence interval conditions. But it's always safe. If you have a null hypothesis, you can just check both conditions, right? The first two are the same. So you've already done both of them. And then if you wanted to cover all your bases, then you could check that you have at least 10 observed successes and at least 10 observed failures. And same thing, do you have 10 expected successes and 10 expected failures from your null hypothesis, right? So as soon as you have a hypothesis, right, stated your null hypothesis, then you can check all the conditions, right? And that's the safest way to play it. So we estimate P by P hat unless, and this is where we're going to talk about that unless, right? I said it before and we didn't really pay attention to it probably, but I said unless we have a hypothesized value for P. Right, so that is H naught is that P is equal to P naught. In that case, we use P naught, okay, instead of P hat. Okay, so if we've checked these conditions, then we know that we can use the normal distribution, which is nice because that means we can calculate Z-scores, and then we have Z-scores that we can use in our Z table to find probabilities, so areas under the curve, and that's what we're going to be doing today. Okay, so step 0, kind of checking the conditions and stating your assumptions, so slight difference, but nothing major. Okay. Once you've checked the conditions, then you can go ahead to step 1, which is to state the hypotheses. It's a little bit tricky, right? Because you've already relied on the null hypothesis from your conditions, right? And so you have already used H naught is that P is equal to P naught in checking the assumptions. Right, so usually this step has already been done, but here you state it, right? So this step has already been completed. All right, so you just need to state it here. Okay. So your null hypothesis is going to be set up in the same way as it was for the confidence interval approach. So P is not equal to P naught. Okay. This is our default. Okay. Is that there's been a change or there's a difference or just kind of not picking a side or a direction that this change is happening in. Okay, and so for the p-value approach, we have a little bit more flexibility and we can test things like whether there's been a change, right? And so if we have a change or a difference or some synonym of that, right? So a change or a difference, or depending on what the question is asking you for, right? Then you might have a null hypothesis that P is equal to P naught. That's going to always be our null hypothesis. And then P is not equal to P naught. Okay. Whereas if you want to know if there's been an increase or some synonym of that, right? So a greater than or an increase, then your null hypothesis is the same. P is equal to P naught. But then now, if you want to know if there's an increase, right, then your alternative hypothesis is that P is greater than P naught. Whereas if you want to know if there's a decrease, right, or it's less than some value or whatever, H naught is that P is equal to P naught, and HA is that P is less than P naught. With an increase or a decrease, we call these one-sided tests, mostly because we're only concerned with one extreme, right? And so these are what we call one-sided tests. They're only concerned with one extreme, are only concerned with one extreme. Okay. Whereas this is what we call a two-sided test, right? So if I just want to know, well, is there a difference, right? Then I don't care if it's less than or greater than, I'm covering both bases, right? So this is what we call a two-sided test. Okay. Okay. So we're going to rely on if we have a one-sided test or a two-sided test later on in step 3 when we gather our evidence, or in this case, find our p-value, right? And so, and there's a lot of p's floating around, right? P's for proportions, but p-values are probabilities, okay? And so, so we'll need to refer back to the alternative hypothesis later in our third step, okay? But for now, let's just have a look at this. Okay. So, so stating your hypotheses, now you have more than one option, right? Whereas if you were using the confidence interval approach, you had to use the not equal to. I will say this, if you're ever unsure, or if you want to feel more confident in your results, right, then use the not equal to, right? So that's still going to be your default inequality. So if you're ever unsure, then you're better off just going with the not equal to. But usually the questions will have you going in one direction. Okay. Or usually, or I shouldn't say usually, or sometimes it'll be actual not equal to. All right. Okay. Step 2 is do the test. Which in the confidence interval approach, it just meant calculate the confidence interval. In the p-value approach, it's going to mean calculate the test statistic. Okay, that's the generic version, because that's going to apply to all these other different types of questions that we're going to tackle. Okay, so in general, we're going to calculate the test statistic. Okay. For one sample proportion questions, the test statistic is a z-score. The test statistic is a z-score. Z is going to look at how far is p hat, so your sample proportion, from your hypothesized proportion, right? And so I'm just going to nab this distribution, and maybe I'll just jot it down again, right? And so here, if I have some p naught, then I'm going to use that in its place. And so I have p hat is going to follow a normal distribution centered on p naught with a spread of p naught q naught over n. If I have this, and if I think back to mu and sigma here, right? Remember, z is x minus mu over sigma. So then now I can translate that. I can translate it to p hat minus p naught, right? How far is this sample statistic from my hypothesized proportion, taking into account the spread, so the standard error. I also want to point out here that on that formula sheet that I've posted, and do I have it here? Yeah, I do. Okay, it's all out of order, but the information is here for you to kind of pick apart and have your way with. So we're in the one sample proportion section right now. And if we have a look at, so we're here in the one sample proportion, it's not really section 6.1, but that's okay. If I'm doing a hypothesis test for P, right, so the population proportion, then here's my default null and alternative hypotheses, right? And it also gives me the Z, which is how you're going to calculate your test statistic, right? Whereas here, if you had to find the confidence interval, notice that the standard error is slightly different in each of these cases. And then next week, we'll talk about the sample size calculation, which is just a fun thing to do and be able to do. So just ignore that for now, okay? But so on this formula sheet, which is just a guide for you, because you're working open book, so I didn't spend any time fixing it. It's all here. I give you the null and alternative hypotheses, or at least the baseline, right? And then I give you the test statistic. Okay. So here in step 2, when we calculate the test statistic, we're going to end up with a Z-score. Now, that's going to feel like we're back in familiar territory, and we are, right? Because I know how Z-scores work, right? I know I can find areas under the curve, and those areas are probabilities associated with this Z-score. Okay, so that leads me to step 3. I think I was calling it like gather evidence or something. For the confidence interval approach, we compared the null value to the confidence interval. Compare the null value to the confidence interval. Okay. For the p-value approach, we're going to find the p-value. Easier said than done. What the heck's a p-value, right? And so let's start there. All right. So a p-value is a probability, and it's the probability of seeing something as extreme or more extreme than what you saw. Okay. It's the probability of seeing something as extreme or more extreme than what you saw in your sample. And then here's the most important part, assuming the null hypothesis is true. Okay, so it's the probability of seeing something as extreme or more extreme than what you saw in your sample, assuming the null hypothesis is true. Assuming the null hypothesis is true. This is a weird concept for a lot of people to wrap their heads around, and that's going to be okay. What I would suggest is just kind of keep working at it, and maybe you have to memorize it, right? Memorize how to find these p-values until it starts to make sense. Okay, so we can visualize the p-values, so that's what I want to do. And here, like I said, this is where we go back and we check our alternative hypothesis to see what our p-value is going to be. Okay, so what I want to do is I want to go back to step 1, and I just want to steal these, oops, these, maybe this whole thing, copy. Okay. So from step 1, right? We've got these 3 options for our alternative hypothesis. Okay, and so if we assume that the null hypothesis is true and all the conditions have checked out and they're safe to assume, then I can draw a normal distribution, right? Because it follows a normal distribution. Okay. So each of these I can visualize by drawing a normal distribution. Okay. Assuming the null hypothesis is true means that the center is going to be at P0. Okay. So the center in each of these is at P0 because the null hypothesis is always the same. It's the alternative that I'm looking at. Okay. Now, the two-sided test, so the not equal to is potentially the hardest one. So I'm going to start and work my way from right to left, and then that'll help us get there. Okay. And so if I want to know if P, which is representing the population proportion from my sample or where my sample is from, then of course my sample proportion has to be less than P0, right? I can't use a value like 0.7 to prove that it's less than 0.5, right? That doesn't work, right? It has to be less than 0.5 to prove that it's significantly less than 0.5. So then in this case, my sample proportion might be somewhere down here. Okay. So then my p-value, the probability, okay, the p-value is the probability, which we know is an area under the curve, of seeing something as extreme, okay, so seeing something as extreme or more extreme, which means that the p-value is always going to be the area in the tail, right? And so here, this area here is my one-sided p-value. And I emphasize that it's one-sided because I'm going to rely on that for my two-sided p-value. Okay. Spoiler alert, I'm just going to multiply it by 2, okay, to replicate it in the other tail. But for now, let's sit on that for a little bit longer. Okay, so how I find my p-value depends on what my alternative hypothesis was. So in this case, if my alternative is that p is less than p naught, then I want to find the area below this z-score that I've calculated in step 2, right? Whereas if I want to know if p is greater than some p naught, then of course my p hat would have to be on the upper end. And same deal, as extreme or more extreme, if I'm on the upper end, that's in the upper tail. So good thing we know how to find these areas, right? Okay. So depending on the alternative hypothesis, right, that's going to help us pick a side. Now, if I want not equal to, we understand I'm only going to have one p hat, right? And it can either be in the upper end or it might end up in the lower end. And so it's only going to be on one tail, right? But what we do is we replicate that in the other tail as well, right? So for example, if my p hat, so my actual sample proportion is down in the lower tail, then I can find my one-sided p-value, and then I can change my pen color to kind of show that, okay, well, it didn't happen here, but I'm going to pretend that p hat also happened symmetrically on the other side, right? Because I'm concerned with either direction. Okay. And so then I have this second tail that I want to look at. Okay. So here, to find the two-sided p-value, we first find the one-sided p-value and then multiply it by 2. We first find the one-sided p-value, then multiply it by 2. Multiply it by 2 to replicate it in the other tail. To replicate it in the other tail. Good. Now we're ready for a conclusion. How? Well, okay. If we think about what the p-value is again, so everything hinges on the p-value, and if I was in this class, I would probably write out this definition of the p-value, maybe on little sticky notes, and just have them all over the house so that you can always see them. And then eventually it'll start to stick, right? That's how I memorize stuff, but it's a little bit much, sticky notes all over the place, but it works for me. And so however you have to memorize this, because I know it's a little bit tedious to memorize, but it is the first step to learning this stuff, right? So I would recommend you memorize the p-value definition, so the probability of seeing something as extreme or more extreme than what you saw in your sample, assuming the null hypothesis is true. Okay, and so now if this probability is really small, right? If the probability of seeing something as extreme or more extreme than what you saw in your sample, right, is really small, assuming the null hypothesis is true, then that's evidence against the null hypothesis, right? So what we end up saying is our conclusion is based off of, okay, if the p-value is small enough, and we're going to have a threshold to determine what's small, right? So if the p-value is small enough, we have enough evidence to reject H0 in favor of HA. Okay. And so for our step 4, or maybe I'll summarize that conclusion. So to draw our conclusion, and maybe I'll do kind of to draw our conclusion, right? If the p-value is small enough, if the p-value is small enough, right? And we're going to have a threshold, I promise, but for now, just in general, right? If the p-value is small enough, we have enough evidence. We have enough evidence to reject H0 in favor of HA. One thing that I want to really emphasize here is you never accept a hypothesis, because there's always, in this case, a p-value chance that you're wrong, okay? And we're allowing what we call an alpha level chance of being wrong, okay? So note, we never accept a hypothesis because in this case, there's a p-value chance of being wrong. Because in this case, there is a p-value chance of being wrong. Right? Depending on the conclusion, but in general, right, there's always some chance of being wrong. In the confidence interval case, if we built a 95% confidence interval, there's a 5% chance that I'm wrong, right? So in the confidence interval, so in a 95% confidence interval, there is a 5% chance we are wrong. Right? So you never ever accept, I don't want to see the word accept anywhere. You can never accept a hypothesis. You can have enough evidence to reject it, or you don't have enough evidence to reject it, but that's all based off of your sample, right? So that's just a note, but it's really important that you keep that in mind. Okay? So to decide if a p-value is small enough, we use what we call a significance level or an alpha level. Okay? So to decide if a p-value is small enough, we use a significance level, which is an alpha level, or alpha, I'll write it out. All right. And so we use this significance level or an alpha level, and the default alpha level is 0.05. And oops. The default alpha level is 0.05. Okay. So I'm just going to tweak this just a little bit, right? We never accept a hypothesis because in this case, there's an alpha level chance of being wrong, right? We're allowing a 5% chance of being wrong, right? So this is actually, but I didn't want to say that then because we didn't know what the alpha level was. I should have introduced it earlier, but I wanted to emphasize it first. Okay, so so there's an alpha chance, or we allow an alpha level chance of being wrong. I'm okay with being wrong 5% of the time is what I'm saying. Okay. And so, okay. That leads me to something called decision errors. And I think I want to finish the conclusion first, and then I'll talk a little bit about decision errors. Because if there's a 5% chance that I'm wrong, right, then I could be wrong, right? My conclusion could be wrong, and there's two ways I could be wrong. But let's just finish off this step-by-step approach first, and then I'll talk a little bit about decision errors. Then I have an example, but I'm also kind of running out of time here. So I'll pick up the pace. No, probably not. So to decide because this is all important stuff, and all the questions that we're going to deal with are going to have the same approach, right? And so it's important that we lay the groundwork here and really spend the time. So to decide if a p-value is small enough, we're going to use a significance level or an alpha level. And the default alpha level is 0.05. Okay, I always get questions. There's no significance level. What am I supposed to do? Well, the default is 0.05. So if it doesn't say, then you're going to use 0.05. So some other options are 0.01, 0.1, and we make adjustments depending on how okay we are with being wrong. Okay, but we'll talk more about that with decision errors. So step 4 is our conclusion. And you'll remember for the confidence interval approach, then we broke it up into 3 parts, and we're going to do the same thing for the p-value approach, but I only want to do the p-value approach for this little blurb here, right? Because you've got the one for the confidence interval approach. So the first thing you're going to do is you're going to compare the p-value to the alpha level, right? And so compare the p-value to the alpha level, right? It's either less than the alpha level or not less than the alpha level. That's easy enough, right? And so it's either less than the alpha level or not less than the alpha level. Okay, and I'm gonna use, so the p-value is less than the alpha, or the p-value is greater than the alpha. You could have the equal to somewhere, and I guess you could put it here in the not less than the alpha level. Okay, and so you're going to compare the p-value to the alpha level. I always verbalize what my p-value is, what the alpha level is, and if it's less than or not less than. And you'll see why I use not less than instead of greater than in the next step here. So then your next step is your conclusion in terms of the null hypothesis. That's the same as the confidence interval approach, but with a twist because we're using the p-value approach. So your conclusion in terms of H naught. And I'm going to copy, or maybe I'll just jot them down again. So we had two options, right? The p-value was less than the alpha. If the probability is less than that threshold, then I have enough evidence to reject H naught. So this means that I have enough evidence to reject H naught in favor of HA. Whereas if the p-value is greater than or equal to the alpha, then, or rather it's not less than the alpha level, then I do not have enough evidence to reject H naught. Do not have enough evidence to reject H naught. Okay, and then the last part is the same as before, right? Depending on if you've rejected H naught or you have not rejected H naught, then you state your conclusion in terms of the question. So your conclusion in terms of the question. It's going to be the most important step, right? Okay, so depending on our conclusion in terms of the p-value and the alpha level and in terms of H naught, right, there's always a chance that we have made the wrong decision, right? And so that's kind of the end of the broad view of the p-value approach. So now I just want to duck out and talk a little bit about decision errors, and then I've got an example. Decision errors, when we either reject H naught or not, right, there's always a chance that we have made the wrong decision. So there's always a chance we have made the wrong decision. Okay. And those are what we call decision errors. And there are two types of decision errors, and they are really confusing in the beginning, or at least for me, I don't know why, but I find that if I use a table, and they have a table, of course, in the textbook, so it's section 5.3.3 on decision errors, and I'm just going to grab this here, copy, and paste it in. So I usually just kind of memorize some version of this table, right? Because we don't know what the truth is. That's why we're doing this hypothesis testing. If we could know what the truth is, then we don't need to do any testing, right? But the truth is either H naught is true or the alternative is true, right? So H naught is false, okay? And so my conclusion, if H naught is true and I fail to reject H naught, then that's fine, right? Then I'm sticking with H naught. There's not enough evidence to reject H naught. That's good, right? Whereas if H naught is true, so if the null hypothesis is true and I reject H naught, that's what we call a type 1 error, right? So it's rejecting the null hypothesis when it shouldn't be. Okay. If the alternative is true and I do not reject H naught, so I stick with H naught, then I've made what we call a type 2 error. Okay. If I've rejected H naught and H naught is false, then I'm fine, right? And so there's only 2 errors that I could make, and the type 1 error rate is the alpha level. Okay, and so the alpha level is the type 1 error rate, right? And so we can adjust the alpha level depending on how expensive or dangerous it is to make a type 1 error. So we can adjust the alpha level, depending on how dangerous or expensive it is to make a type 1 error. How expensive or dangerous it is to make a type 1 error. Type 1 error. That's when I reject the null hypothesis. So I say there is something going on here when there isn't, right? And so there's lots of different scenarios, and the textbook has a thorough example of sending people to jail when they are innocent and that kind of thing. And so that might help. A type 2 error is usually just the result of not a large enough sample size. So we don't really focus on type 2 errors, but type 2 errors are typically the results of sample sizes that are not large enough to detect a significant result, of sample sizes, or of a sample size that is not large enough. So there's not really anything we can do about the type 2 error as much. Okay, with just I know I'm cutting it close here, but I do want to do an example, and it's also from the textbook, and let's see if I can find it. It's at the end. And I wanted to do this one because it talks about the majority, and I always get questions about, well, what's the majority? And I know it sounds silly when I say it, right? But I know you're going to come across a question where it says, okay, a majority, how the heck am I supposed to know what that is? A majority is more than 50%, right? And one bummer about this example that I want to use is that the wording is really strange. So I'll try to kind of cut through it a little bit quicker. Okay, so the question asks, do a majority of US adults, and so a majority is, let's just highlight here, and maybe I'll bump this down. A majority is more than 50%. Okay. Do a majority of US adults believe raising the minimum wage will help the economy, or is there a majority who do not believe this? That's kind of a weird question, right? Is there a majority here or a majority there? Okay, so we'll try to pick this apart, and I try not to use confusing questions like this, but I do expect you to know what a majority is, and it's more than 50%. So a Rasmussen Reports survey of 1,000 US adults found that 42% believe that it will help the economy. Okay, and so I can't use 42% to prove that a majority will help, thinks that it will help the economy, but I can look at the opposite and say, okay, well then, what is it, 42, so 58, 1 minus 0.42 is 0.58. So here, uh, 0.42, think that it will help the economy, and 0.58 believe that it won't help. Okay. Presumably. So now if we're trying to prove a majority, then we're looking at these, and I can use 0.58. Is 0.58 significantly more than 0.5? Right, that would be my question. And so now I'm going to formulate my hypothesis in terms of the won't help. This is a weirdly worded question, and it's something that's why I wanted to go through it. I was just hoping I'd have more time to do it. So make this a success for this question. So what does that mean? It means that p hat, p hat is 0.58 and q hat is 0.42. I'm also given that the sample size is 1,000. And I should check the conditions here, but I'm gonna just run through it. So step 0, guess I have to read the entire question first. I've read it. Can't assume that you have. So conduct an appropriate hypothesis test to help answer the research question. So step 0, we're going to do a hypothesis test with the p-value approach, even though it doesn't say so, but the default hypothesis test from now on is going to use the p-value approach. And so I can check the conditions, which will mean that I'm going to need to have some idea of what my null value is. So this means that my null hypothesis is that p is equal to 0.5, right? So 0.5 is my null value. So step 0, check the conditions. It doesn't actually say that the sample was randomly selected, so we assume the sample was randomly selected. We assume the sample was randomly selected. And n equal to 1,000 is less than 10% of all US adults. Right, that's the optional one, but may as well throw it in there. And now I want to know, okay, how many expected successes do I have? If I assume that it's a 50-50 split, then I have n times p naught, which is 1,000 times 0.5, which is 500, which is greater than or equal to 10. And same thing with n times q naught, 1,000 times 0.5, which is also 500, which is greater than or equal to 10. So now I'm ready for step 1, which is to state the hypotheses. I've already informally stated the null hypothesis is that p is equal to 0.5. And what I want to show, right, because even though I was given the 42% or the 0.42, I've tweaked it so that it would match how I want to solve this problem. So p hat is actually 0.58, and I want to know if it's a majority, so if it's more than 50%. So here, what that translates to is that HA is that p is greater than 0.5. Now, usually I make a little note here that this is a one-sided test. I don't need that until finding the p-value, right? But that tells me that, okay, the p-value is only going to be in one of the tails. Step 2, do the test. So that's going to be calculating z is equal to p hat minus p naught over the square root of p naught q naught over n. So z, and I guess I can put it on new page. Z is 0.58 minus 0.50. over the square root of 0.5 times 0.5 over 1,000. And I'm just going to skip straight to the good stuff here. 0.5 times 0.5 divided by 1,000. Take the square root of that, and then 0.08 divided by that. I get a Z of 5.059644256. I would round it to 2 decimal places if I was using the Z table, but in this case, I already know my Z table ends at 3.49, so there's not a lot I can do here. But step 3, find the p-value. Well, I can visualize it if you find that it helps, right? Centered on 0.5, and I found a sample proportion of 0.58, right? Which is at Z is equal to 5.06, let's call it. So then this area, this one-sided p-value is less than 0.002, right? And that's from the Z table, right? From the Z table. You could say it's approximately 0, but it's nice to have a value that we can use there. Okay. Usually you would find a value, but if it's off the table, then you don't have one. Okay. So step 4 is your conclusion. We compare our p-value to our alpha level. The default alpha level is 0.05. There is no alpha level in the question, so I have to use 0.05. And so since the one-sided p-value, and I just like to show off everything that I've found, so why not? The one-sided p-value is less than 0.0002, it is also less than the assumed alpha level of 0.05. Becomes kind of a run-on sentence, but what does that mean? Which means we have enough evidence to reject H0 in favor of HA. Which means we have enough evidence to reject H0 in favor of HA. What does that mean in terms of the question? Well, this is where I usually reword the question as an answer, but this question was worded so strangely. We were testing if a majority of US adults do not believe that raising the minimum wage will help the economy, right? So kind of a weird question here, but therefore, a majority of US adults, I guess, would be do not believe that raising the minimum wage will help the economy. Do not believe raising the minimum wage will help the economy. Oof. Okay, good. It was a weird question, and I wish I had more time, but hopefully that helps. Oh yeah, so in your rough work, no, it's just for you to kind of support your answers. So if you find that it supports your answers or it's something that you've written anyways, then you can submit it, but you don't have to write the steps, but you do need to have your conclusions somewhere, right? If that makes sense. Okay. If you have any questions, let me know. Otherwise, I'll stop this recording and good luck on your quiz tomorrow. And I'll see you next week. Stop this.